Okay. Don't want to release notes. It's visible. Nice. Okay. So you can go play with this notebook at home, but what we did was in this notebook, again, for this particular example, we went ahead and coded the whole thing end to end. So we wanted to play with all these knobs. So we went ahead and implemented. Okay. So first we implemented some linear transform because our KLT is basically a linear transform. You have to define some vector quantizer because you need a quantizer at the end of the day after you get these streams to actually do lossy compression. And finally, we also did this transform VQ encoder and decoder, which first transforms the data using a linear layer and then vector quantizes each component separately. Okay, so I'm not going to go into this code because it's not really pedagogical in the sense that if I explain it, it won't really make sense. But I highly encourage you guys to go home and look at this code and see if you understand this flow end to end. So this literally implements the whole process which we discussed end to end for the example. So for example, in transform VQ encoder, you can see that there is a loop over each coefficient ID. So that's like going over each stream independently. And then for that stream, you will do some vector encoder, a VQ encoder, right? Scalar, you can think of it as a special case of vector quantizer. And so you would vector quantize these symbols, and that will actually finally give you some bit array, coded bit array. And then you also have to basically tell the length. Otherwise, like if you have two streams, if you don't tell the length, and you can't concatenate this, you don't really know when the second stream is starting, right? So that's like the similar idea. We have looked at it before in various different settings, right? So you also might want to encode the length of each stream so that you know when the second stream is starting. You can decode it accordingly. And then your decoder does the exact opposite. So again, it basically goes in the inverse loop where it decodes each transform component. So again, you have a for loop. And then within each component, it does this VQ decoding. Yeah. And actually, the implementation of VQ encoder and decoder is also it's very simple, but I would again say, like, if you haven't done it, go do it. It will give you a very good understanding of what's really happening, right? I would even say, like, you can take this as a understanding homework problem. Don't look at this code, try to implement this, come back, see if it makes sense. Okay. But in any case, so we went ahead, and so this is the source we were looking at. And we did some experiments on this source in the spirit of this class. Like, okay, let's actually play with these knobs and see what we get. Again, you can regenerate the results from the notebook, but let's come back. Okay. And so let's discuss the performance of what we looked at. Okay. So what I'm showing here is, first of all, my rho is now 0.9. Okay. So this value is 0.9. The higher this value is, the more correlated your initial components are. Okay. Okay. So the first row just shows a vector quantization experiment. So we are not doing any transform. I'm fixing the bits per symbol as 1. So in all of these experiments, it's the same idea from what we just discussed. So my bits per symbol is 1. Okay. So the first knob which I can play with is the block size, right? So this is just doing vector quantization, increasing block size. All of these experiments are at a fixed rate. Okay. So this makes sense, right? And so obviously as you increase the block size, your distortion decreases. Not surprising, but your complexity also increases, right? So now you have to generate code book in 4 dimensions. You have to figure out points in 4 dimensions. What the second block is showing is a transform coding vector quantization experiment. So TC is for transform coding. So first you transform, and this is using the exact same transform which we just derived for this example. Okay. And now after you have decided that, so in all of these examples, I'm fixing the block size of the transform. It's just 2. Again, bits per symbol is always 1. And then I can decide my bitrate split between components, right? Like exactly what we discussed. So I can give equal bit rates to each of them. I can give maybe more bit rate to the second one, or maybe more bitrate to the first one. 0 just means I throw away that component entirely. I don't even care. And so what do you guys think looking at? So this is the, again, all of them have rate 1. This is the distortion. What do you think happened here? So I would say, like, look at this number. So this was 0.163. We are fixing block size 2. Everywhere we are fixing block size 2, each of the step for the transform coding. And 0.163. And for different bitrate splits, I see very different levels of distortion, right? So what's happening? Not a trick question, just say it out loud.
First component has a lot more variance, so if we dedicate more bits to it, we get lower distortion. If we put our bits in the second, then it goes really high, as we see in the second one.
Exactly. So this is now a very concrete example of what we have been discussing, right? So what we see is, if I give more bitrate to the first component, which had higher variance, remember, like, it had 1 plus rho sigma square, right? Variance, whereas the second one had 1 minus rho. In that case, I get something which has much better performance than this 0.163 with equal complexity, right? I'm still, so obviously, okay, not really equal because I have to do the transform step extra, but equal quantization complexity. Whereas if I did exact opposite, if I gave more bits to the symbol which had lower energy, like stream which had lower energy, I suddenly pay a huge penalty. And clearly equally splitting bits between them is not the optimal thing to do. Okay? Everyone's with me? Okay. So now in the next one, I'm going to change the row. And the question really is, what do you expect? If I increase the row, do you expect to see more benefits or less benefits? Okay, more. Let's have a show of hands. Like, we can vote this out. This is a binary choice. So I'm going to increase row. So I'm going to increase the correlation. And the question which I am asking is, what do you expect, like the transform coding VQ, when I give unequal bitrate splits to the two components? Do you expect more advantages or less? How many of you say less? How many of you say more? Okay, at least half of the class is neither more or less, so equal, I guess. Okay, do expect more, right? Because the more correlated the sources are. So there are two things. One, it's harder to get good performance from them by using lower dimensional vector quantizer, right? But the main point is, as you change your row, remember the variances were 1 plus rho sigma square and 1 minus rho sigma square, right? So as rho increases, my gap sort of increases, right? So that's sort of allowing me to do more of this water filling stuff, right? Like, I want to have more and more gaps so that I can just throw away the lower variance component sooner rather than later. Correct? And so here what I'm showing is the same expression 99. And now here you can see that, okay, this is 0.107, but now when I do bitrate split between 2, 0, my distortion just goes down to just 0.03 compared to 0.107 here, whereas here it just barely beat it, right? 0.163 to 0.122. And also, like, you can see how high this gap really is. Like, if you allocate more bits to the component with higher variance versus lower variance, or higher energy versus lower energy. Okay, one point I didn't say, but you can see that even in this, like, okay, going to block size 4 still beats this. So again, like, so the point really is vector quantization, you shouldn't forget about it. It is really powerful. It's very compute intensive. So you have to be selective about when to throw sort of rocket at your problem versus when you can just get away with an arrow. right? So what transform coding is allowing you to do is at times letting you get away with an arrow, really. And so this is like same experiment, but this time I reduce rho to 0.5. And actually in this case, even while giving the maximum bitrate split, I'm not able to beat it. And actually this I'm going to leave as a take home, think about it, ask in office hour or on ed. But it's actually not surprising that 2.0 is not beating. And I'll give you a hint. So question really is, why transform coding doesn't beat? So I'm not filling in the variables, but you know the variables. Doesn't beat VQ for rho equals to 0.5. And I'll give you a hint. Our gap, our sigma 1 is 1 plus rho sigma square, and our sigma 2 is 1 minus rho sigma square. And at this point, these are Gaussian IIDs, right? You actually know exactly the solution to this problem. So given a total distortion and a total rate, we have worked out the exact solution to this problem. And so when rho is decreasing, basically you are probably in a scenario where variance is not in the middle of the two variances. Maybe the total rate, total distortion which is there is below the first component also. So you can't throw away the first component completely. So again, this is like repeat of water filling, right? So remember in the water filling case, like we don't always throw away the component with lower variance, right? There is a case when your distortion is lower than the 2 sigma, you still want to keep, but you will give it a lower rate. So in this experiment, I didn't find the correct split. That's really the intuition. You could have worked out the exact bitrate split, and then that could have beaten the thing. Like go home, think more about it. Actually try to work this out exactly like the previous question, and that will give you some intuition. Any question? Cool, everyone's with me? So I hope this example kind of gave you a better idea of what's really happening with the transform coding. But now let's get into the practical aspect of it. Nobody actually uses KLT in practice, even though we did all this. And we talked about it a little bit, but now I hope working through this example gave you a better intuition why we don't do it. So your KLT is basically dependent on the statistics of input, right? Like recall we had to, where is it? Yeah. Recall what all we did for this example. We first had to figure out like a distribution, given the samples ideally, right? Or we could have tried to estimate the covariance matrix directly, which is a function of the input data. What that means is like I have to recompute this every time I get a new input data, right? I have to keep redoing this computation. And moreover, this computation is not trivial, like in the sense that it costs you to do the eigenvalue decomposition. Like we didn't really talk about the complexity aspect of it here, but it costs you some compute time to do all of this, right? So it's not really ideal. You don't want to add an extra compute time at each step of doing the transform. And that's really like one of the main issues with the KLT, right? Another issue which I think one student pointed out last class is in practice, we don't even know sigma. So we have to estimate it and there'll be some errors also because of that. Though I think that's still, I would say, the secondary concern. The primary concern really is it's computationally intensive and slow. Yeah, so we can't really work this out. And so this leads us to the practical transforms. And the question really is, I don't want to keep recomputing my matrix again and again, my matrix T for new data. So can I come up with some structured transform, which is a way of saying, can I come up with a fixed matrix, so as to say T, which doesn't change with the data, which is easy to compute, right? And basically has good energy compaction properties. So if your matrix T doesn't decorrelate, doesn't do it energy compaction, then that's basically a useless transform. You won't be able to exploit it for the compression part, which we saw later, right? Again, so in the previous example, if you recall, one intuition is as my correlation increased, I basically got two components with a bigger gap in their variance. And that allowed me to compress my source really better, right? So ideally, I want this energy compaction thing to happen for my underlying compressor, for my underlying quantizer to take benefit. And so we are going to talk about something called DCT, discrete cosine transform, a little bit. And it's amazing, like it's basically used in so many compressors out there. And if you are familiar with Fourier transforms, discrete Fourier transforms and alike, you can think of it as a sibling of DFT. Basically, it's another one of the frequency transform. And this is really, really funny. So Kedar, I think, found out this. This was, was really nice. So he's the author who came up with the DCT transform idea. And you can look at this article. It's actually very fun read, like weekend fun read. And so these are like two excerpts from that article. And so if you look at the first one, what Nasser says is like, what intrigued him was the KLT was indeed the optimal transform, right? So we know KLT is optimal. And yet there is no efficient algorithm available to compute it, right? So that's really the issue. So this guy said the same thing. And then as such, the focus of his research was to determine whether it would be possible to come up with a good approximation to the KLT, which can be computed efficiently. It is essentially what we want to do. And he came up with this idea of DCT, which is used everywhere. So clearly he was very successful in his endeavor. And then even more funny, and this is like an anecdote to research. So if you are doing your PhD or research, don't get demotivated if you believe in your idea, but nobody else does. Because much to his disappointment, in his case, NSF didn't even fund their proposal. So like, and again, like DCT, basically, as Shubham said, like whenever you are opening some image or some gzipping, when you open any compressed file on your computer, at least multimedia files, most likely you are running some DCT transform on that every click. Every time you have an image loading on your browser, there is a decompression step happening, and DCT is somewhere most likely involved in that step, whatever multimedia it is, be it audio, video, YouTube, Netflix, Spotify, it's everywhere, right? So it has clearly made quite an impact. And so after this fun detour, let's get back to this question of the practical transforms, right? Like, so we want to come up with the structured transform. One second. Okay. And in practice, there are like, you will see a lot of options for these transforms. So I just said discrete cosine transform is just one of them, but you can think of discrete. So if you have done signal processing in your life at any point, you would have heard some of these terms, discrete Fourier transform, wavelet, so on and so forth. Actually, there's a very nice list on Wikipedia for like all the sister, I would say Fourier based transform. It was nice to look at it. A lot of people have spent a lot of time in thinking of all these different transforms, and they have like very strong mathematical properties. We are not going to redo the signal processing part. I'll just take some time to quickly give you intuition of what these are doing, and we'll refer you to like more signal processing literature if you want to learn more. So I want to say upfront that this is going to be a hand-wavy discussion of DCT. DCT is actually a very, or like all of these transforms are actually have very nice mathematical properties. You can study them very rigorously, and there are courses, whole courses which do that. So I'll encourage you guys to take them if you like. But these are the basic ideas which are really important for the compression when it comes to these transforms. Okay, point one is most of these transforms are based on the idea of the orthogonal or orthonormal basis, which we have looked at. So we are still working with the same idea. Many of them will exploit the sparsity of signal in some basis. By some basis, I mean some transformation, right? So for example, you'll see that DCT exploits the sparsity of the signal in cosine basis. What that means is if you have some input symbols X, you apply DCT to it, you get this DCT frequency components. If it's a natural signal, most likely you will see that you'll try to have sparse transform components. So you'll have transform components which are already 0. So that sort of allows you to throw them away. So they will have very low energy, right? So that fits very well with what we want to do. They give you the energy compaction property. And the main idea why these work, so obviously, okay, like Nasser said, okay, DCT was also a good approximation to KLT under certain settings. We won't really talk about that here. But one key takeaway why these things works is because of the natural signal statistics. What that means is that if you look at a natural image, a natural audio, right, like whatever image I'm seeing here, a natural video, and then you do some frequency transform of it and you try to see, okay, what are the frequency components, you'll see that most of the energy of these symbols will lie at lower frequency compared to higher frequency, right? So you have this natural content which basically doesn't have a lot of energy in the higher frequency components. And then using one of these transforms, you can exploit that, essentially. Okay, so this is really one of the key ideas why this constant transform works. It works because your signal itself has statistics, and you can use this transform to extract that property that, okay, it is sparse in higher frequency components. So when I transform it, I'll get lower values of these transform components. Okay. This is really, I would say, like, in some sense, one key intuitive jump. It wasn't obvious. You need to know that your world around you is sort of low pass filtered, so as to say. Yeah. And actually, it's just not this. So this kind of gives you the Gaussian water filling kind of intuition of why these transforms work. But in reality, like a lot of these compressors, like when you actually see how they throw away the bits for different components or how they assign bits for the different components, it's not just based on energy. It's also based on who is consuming the final lossy compressed signal, right? So for example, images or audio, these are to be consumed by humans at the end of the day. And we as humans also don't really see high frequency signal. So if you have like a lot of high frequency signal in an image, so if you have a lot of noise, you just do a low pass filter of it, you won't even see that noise if it's extremely high frequency. Similarly with audio, like our frequency range at which we hear is set 20 hertz to 20 kilohertz, but in reality very few humans actually go that wide. But for this discussion, let's say 20 hertz to 20 kilohertz. So if you have a signal and it has a lot of bits or a lot of components which when you do frequency transform above 20 kilohertz, you don't need to store it. Like no human is ever going to hear it. And so far we are not compressing, I guess, audio for dogs and animals. So we should be okay. It's for us. So that again gives you a motivation. Even if you have some non-zero, let's say, energy in components above, let's say 20 kilohertz, you don't want to keep it. You will throw it because it doesn't matter in practice. Your distortion really, the key idea there is, the key switch which happens is your distortion, mean square error is not the right metric. At the end of the day, like in some sense, mean human error is the right metric there. Right? And we are not going to talk about this today at all. There's actually, in fact, a whole lecture dedicated on this aspects because this is not typically covered in a compression, but it's very important for compression, but it's typically not covered in like information theory kind of classes. So we'll talk more about it after Thanksgiving. But yeah, there are really two reasons working out. So one is more on the KLT side, but the other is on the human side. And if you don't remember anything else, like this is the key takeaway, like compress the high frequency components more, you're gonna be fine. And so DCT actually is one of the, again, like I said, most popular transforms in terms of compression. In compression world, it's really popular. But again, like depending on your application, you might hear about DFT, many other transforms. What DCT is, and we'll look at some examples just right now. Let me just give some summary if you have never heard about DCT before. It's basically discrete cosine transform, right? So it's basically values of cosine function at discrete points. It's just basically that. Again, it's linear. In fact, it is orthonormal. And again, like it's just a variant of DFT. So you can think of the outputs of DCT as again doing some frequency analysis. So you're just breaking down your signal into different independent frequency channels. It's a real valued transform. So this is where it's actually different from the Fourier transform. Like FFT can lead to imaginary values, but we don't want our transform components to lead into imaginary values, really. And so, yeah, so this is just like another property of DCT which helps us. And finally, it's a lossless transform. So again, like we have the TT inverse property working for us. So we can just plug and play. And then various versions of DCT exist. So if you actually go look at the literature, you'll hear something about DCT1, DCT2, DCT3, DCT4. It's okay. All of these are like very, like, they basically differ in the boundary conditions of how these matrices are derived. Yeah, don't worry about it from the compression angle. We'll just think of DCT2, which is like the most. So DCT2 is mostly what's used in many of the practical compressors and scenarios. So, yeah. So again, let's build some intuition for DCT2. And again, this is there in the transform coding. Oh, it's reloading. This is again in the transform coding notebook. So you can go home and look at it. We'll put it up on the website. Okay. So I've been hand wavy. I never really defined DCT. I don't think that's the point of this class again, but I have put it here, what your DCT transforms look like. So if you want to go at home and look at it, please do. This will revise your signal processing. So let's start and let's first look at the DCT transform matrix. So again, you have to start with some block size. I can do this. Interesting. Okay. So you have to decide some block size, right, over which you are going to do. So here I've decided 8 as the block size. So my DCT transform matrix is going to be something like 8 by 8. So I just literally wrote down those formulae for the DCT transform, and I used that to generate this 8 by 8 matrix. And the value in each of them is the value which you are going to multiply with that matrix. So what you see is that like the first row is basically constant value. So if you were to multiply this with a vector, the first component of the transform will just be the average, so as to not exactly average, some proportional to the sum of all these components, right? And then as you go down, you see some colors changing, some wiggliness happening. So yellow here is positive, blue is negative. It's almost symmetric. But really, like, as I said, like, if you think of each row of the DCT matrix, that's basically coming by like discretizing some cosine waveforms. Okay. So what I'm showing here is again, so this is row 0. So the first row of our DCT matrix, and that's all some constant value for the 7 different components. Then here, this is row 1. And now you see this is like discretized version of a half of cosine like waveform, something. Right? Like the blue points are the actual values which exist in the transform, and so on and so forth. So you can see this is like increasing frequencies. Red is just the continuous cosine curve. It's increasing frequency, and then you are basically taking 8 samples out of it. And that basically defines the 8 rows of DCT. So as you are basically going down in terms of your transform components, you are looking at, in some sense, higher and higher frequency, right? Again, this is going to be a hand wavy thing. You can formalize all of these intuitions and numbers, but this is just to like give you a quick sense of what DCT is. Okay, so now once you have looked at the transform, we can actually use this transform to do the forward transform and the reverse transform. So these are just function which takes some signal, and again, like here I've just spelled it out. There are also SciPy functions, etc., which you can use in practice, but this is for pedagogical reasons, so you can just write down these formulae. Nothing fancy. Okay, so now let's look at some of the examples, like what happens when you apply DCT in various different cases. Okay, so the first example is that of a constant signal. So suppose you had a constant signal with constant values. You can look at the DCT, and there you will see that, oh, it peaks at the 0 value, right? And that makes sense because here you only have a constant frequency, nothing else. And then when you take the IDCT of this transform components, DCT, you recover back the original signal in green. Yeah? Everyone's following what's happening here, roughly? Yeah? Okay. Okay, so now in the next example, let me just take some sinusoids with various varying frequency. And so this is now my input signal. It has some frequency. I look at its DCT coefficient. It has value 0 for most of the high frequency components, so higher values of my DCT, but it somehow some peaks at the index 2, so like component peaks. And then when you apply the IDCT on this DCT, you recover back the original symbol. And what you see is like on the left, as I go down, I keep increasing the frequency of my signals. And what you see is that the DCT coefficients, now the energy in the DCT coefficients is moving towards right. Right? So it's like, again, your DCT is tracking the frequency of the signals in substance. The higher the value of the DCT component in your transform side, the higher the component which is non-zero in the transform side, that means higher the frequency it has, the input signal has. Okay, so again, it's tracking frequencies is what I want to say. It's not really a delta function because all of this depends on, as soon as you go from continuous to discrete, a lot of things starts depending on the boundary conditions and exact samples. If you know about it, great. If you don't know about it, don't worry about it right now. Okay, so now let's look at another example where we just have a general signal. I just made some triangle-like signal. I did its DCT. So again, it's 8 by 8. So I have 7 transform components. Now for this signal, I see it has more low frequency component, but there is some non-zero high frequency component. For example, this component at 5. You can't see my pencil, right? Okay. So this component at 5, it's not really 0. There is a small stem. So there is some small value, but it's mostly 0 at the higher frequency components. And again, when I do the IDCT of this thing, you get back the same signal. So far, so good. But now you guys know what we are going to do, right? So we are not going to keep the whole DCT when we are doing the lossy compression. We are going to throw away. And the way we are going to throw away is, again, let's just use our intuition. We don't have a theory right now to help us. Let's just use our intuition. What will you do? You will like throw away the components which have very low power, right? That's like one way to compress. And because then you don't have to worry about a whole stream, essentially, of things to quantize. Correct? And so let's just do that for this particular signal. And so what I'm going to do is, basically I'll have a threshold. And whatever components lie below that threshold, I'm going to just put it to 0. Okay? So the first one is threshold 0. So I basically keep all the components. And you see that the green reconstructed signal is matching exactly. But now I went ahead, I took some very small threshold, like 0.25. So everything in this plus minus 0.25 window, I'm going to put it to 0. Actually, just this guy goes to 0. So that was non-zero here, it's 0. You can't even see it. And you get this recovered signal. So green is the reconstructed signal, red is the same original signal. So now you see, like, okay, it won't match exactly, right? Because DCT, IDCT would match exactly only if you have the same components. But now you see, you introduce some small error. Okay. So, run the experiment. Let's keep increasing the threshold. 5. Now you see at 0.5, all of my high frequency components have gone to 0. And I'm actually just keeping 3 components instead of 8 components. But still my errors seem like somewhat controlled. It's not really that the green signal looks super different from the less red, right? Obviously, you are introducing distortion, but it's not too much. Then you keep increasing, keep truncating. At some point, you basically keep you keep nothing, all the DC signal. At this point, obviously, your errors are just over the roof, right? If you just keep the first component, that's basically saying, oh, I'll just transmit the average of these things. So that's not really useful. But maybe somewhere here, at threshold 2 or maybe at threshold 1, where you're keeping just 2 or 3 components, depending on the scenario, these errors might be more manageable, right? And so this is really what DCT does, right? So you're splitting it into transform components and you're throwing away maybe components. So in this example, we completely threw away. But again, like we discussed in the previous example, where rho was 0.5, maybe you don't completely throw away. maybe you compress some components more versus some other components less, and that's very common in a lot of practical transforms. Okay, and like this notebook is available, so you can go over it. Any questions? Because after this, we're gonna just go 5 more minutes and have some fun. Like we're gonna collect everything which we have learned and make our first lossy compressor. Yeah.
How is it different from Fourier transform?
How is it different? You can think of it as a sister like transform. Basically, the boundary conditions are different. So in Fourier transform, like here you assume symmetricity, and it's basically a different transform, very similar like Fourier transform. But in Fourier transform, unless you have, I think the real reason is it comes from the block conditions, boundary conditions. So when you have these boundary conditions, you want continuous signals. And in Fourier transform, you can show that DCT accommodates the boundary conditions better when you break down in blocks. Maybe I'm not able to express it very clearly. I'll answer it better after the class. You want to?
It's like for constant type signals, I think DCT is more concentrated at lower frequencies than the DFT.
Yeah.
Because cosine is like
Flat, yeah.
versus sine sort of sharp,
Yeah.
something like that.
So basically sine has a higher derivative at 0 actually. So in boundary conditions, so what happens is you have this signal, but you are chunking it, right? So for example, in this 8x8, I won't really always get 8 signals, right? I'll have a continuous stream of symbols. I'll chunk 8, then chunk 8, then chunk 8, right? And so what you want is when you do this and get the inverse transform, you want the boundaries shouldn't be like, oh, there's a sudden jump. Imagine you had first block, last element as value 1, and similarly again, a bunch of values 1 in the second block, initial component. You want that constant to remain constant across the blocks. And DCT, like again, it's a bit mathematical, like I think I'll explain it, I'll post this on it, a much more detailed answer after the class, but DCT ensures that this constant signal remains constant when you throw away compared to DFT, which can lead to huge shifts. And so you can imagine if you have huge shifts and you have some continuous signal, that might be very odd to see even in lossy compression. That shows like, that's a very common artifact called blocking artifacts because you see things messing up at the boundaries. Let's maybe go a little ahead and I'll post much more detail. But for now, if you don't know anything, you can think of it as a sister transform of DFT. Okay. So I'll just go five more minutes. I do want to do this. This is really the pipeline for our bare bones practical lossy compression at this point, right? So we start with some symbols xn. You do some transform, you get yn, you quantize this, you get some codebook vectors. After that, you have to do entropy coding, right? So you do lossless coding of these codebook vectors, whatever you get. That gives you the bit stream. At the end of the day, you have to get to the bit stream, and this determines the rate. And then on the decoder side, you first do exact reverse steps, right? So you first do entropy decoding. That gives you the codebook indices, which you can use to dequantize, which gives you some recovered transformed vectors. And finally, you do the inverse transform to get back your original signal. And your distortion is between what you started with and what you ended with, right? So this is like the rate distortion trade-off. And the key point to notice, the only lossy step here is quantize, right? And this is really, like I would say, this is like the bare bones practical. At this point, you already have, if you do all these steps, you have a practical lossy compressor. In fact, what we will see in next lecture, JPEG essentially does this, and it really optimizes each block to its fullest. But it's essentially this exact block diagram at its core. Okay, and so we have lots of design decisions, like you can choose different transforms, you can choose different quantization, you can choose different entropy coding schemes, and we have given you some of these in the class, right? But again, something to note, there are many other options which we might not have covered, but so we have already covered like some options for each of this. So let's just go ahead and look at one. So we're going to go and look ahead at an audio compressor, which basically does this exact same thing. And this thanks to Shubham for having this notebook. So our audio compressor is going to do exactly these steps which we talked about, sorry. So we are going to do transform, in our case DCT. We are going to quantize using just a scalar quantizer. And then we are going to do, we are actually not going to do entropy coding, but we are going to look at it. Okay. So let's just look at this notebook. Okay, so this is like setting up some basic code. You want to be able to quantize and quantize. You will do DCTI, DCT. You will do something like low pass DCT, which is exactly the thing which we looked at. In some sense, like thresholding the components and keeping the others to 0. And then there are a bunch of other helper functions. And so in a simple audio compressor, you can actually play with 2 components, right? You can play with the frequency cutoff, which is like saying, okay, how many components do I actually keep? Or you can play with the number of quantization levels, and those will have like different effects. So this notebook has lots of quiz questions, so go again do attempt them. So let's just start. So I have already loaded the data here. And so what you see here is the transformation for one of the file. On the x-axis is like the frequency component, so you can think of these as independent transform channels. And on the y-axis is the energy. And if you see, for this natural signal, there is a natural cliff. Maybe I should be able to zoom out. Okay, I'm not able to zoom this out, but yeah. So you can see that, like for this whatever audio signal, your energy suddenly drops from this point onward. So this was the point where natural signals automatically have their statistics such that there is low energy at higher frequency. Yeah. And so we can do 2 things. We can either throw away, we'll decide to throw away all the components above a frequency, or we can decide to discretize each component with more or less number of codebook vectors, right? So, okay, let's just hear this out. I don't know if this will work. Let's see. Okay. So this is the original audio, and again, if you've done homework 3, you know one of the instructors is probably Pokemon fan, so you can guess later. But okay, you can hear the whole thing. So this is just the original audio. I wanna be the bear. Okay, and so first let's look at what the low frequency cutoff version of this audio looks like. Audio is coming from here. Okay, so you observe that, okay, it still was like the Ash wants to be the very best, but was somehow very dull about it, right? Like we removed the high frequency components, it sounded very dull. Okay, so that's one way to do lossy compression. But I could also just reduce the number of quantization levels, keep all the frequencies. Let's do that next. I wanna be the very best. Okay, so in this case, you can hear like all the instruments and the high frequency stuff, the treble, the bass, but there was like a very static noise behind, right? Like there was like, let's just hear it quickly. No one ever was. It's like kind of going on, right? So that's basically being introduced because now you have increased the quantization level. So you see how playing with these 2 different knobs led to different distortion in some sense, right? Like very different sounding distortion. But what you can do is like you can go ahead and plot it as the rate distortion curves, which we have looked at before, right? So on the x-axis is rate, y-axis is distortion, and we are doing many different colors at different frequency cutoffs, different symbols are different quantization level, okay? And this is what people also do in practice. You would actually, like this is what I was saying, if you're a streaming service, you will actually encode this Pokemon in various of these forms. And you will basically keep the points which give you the lowest distortion at any given rate. So what you will see here is at low bit rate, you can't see whatever I'm drawing there. Okay. So at low bit rate, you have colors which are changing, right? Whereas at high bit rates, like the things, so this black dot is the Pareto-optimal black line. You see the number of quantization levels are changing, the symbols are changing. So what's really happening is that at extremely low rate, you are benefiting by including more and more frequencies. But after a point, it doesn't really matter to include that more frequency because that anyways has low energy. You can just throw it away. Rather, really keep the frequencies which are low in much, much higher fidelity. Right? So this is like this. Every streaming service has these are called like encoding tables. And you will have some version of this, people playing with these knobs in practice to figure out like what's the optimal way to compress my symbol. Okay. And so this was like we did some transform and then quantized. But let's say your friend who never took this class actually didn't transform. He directly quantized, right? So this is similar to the example which we looked above. In that case, basically, you get these black dots, which are much higher in distortion. So now you can see for basically similar power of quantization, you get much higher distortion compared to if you were doing transform coding. I think there was an example. Okay, maybe I missed this. Sorry. So this, yeah. Okay, yeah. So, yeah. I think this is an example. Let's just hear it. Yeah. Exactly. So this is again the low pass one. So with transform and quantize, and the next one is just direct quantized.
I wanna be.
Okay. And this is the second one.
I wanna be the very best.
Okay. So here I tricked you because both of these symbols basically have the same MSE. So they roughly sounded similar. But if you look at the bit rate, the direct quantization one took 160 kbps. So it's here, took 160 kbps, whereas transform plus quantize one took just 86. So similar sounding, but transform clearly helps. And just the last thing which I want to show, and I'll end the lecture here is, okay, this was a bare bones lossy compressor. It was literally that pipeline. We did DCT, we did some quantization and we worked around. But there is a very popular compressor, MP3. So we might want to compare how our compressor performs with respect to MP3.